My name is Gauss-Bonnet, and first of all, I would like to thank our organizers for this great event. And after that, I want to thank all the mentors and mentors for this great event.
Hey, pardon bir saniye özür diliyorum ama biz çok duyamıyoruz ya Ilgaz seni.
Benden mi kaynaklı yoksa sistemden mi kaynaklı? Çünkü sınıfta duyulduğunu...
Belki biraz daha yaklaşsan olur mu?
Evet, bu böyle daha iyi mi?
Evet, daha iyi. Çok
Tamam.
teşekkür ederim.
Hello everyone, my name is Ilgaz. First of all, I would like to thank to all our organizers for their great effort. And after that, I would like to thank to all mentors and mentees for their hard work. And of course, finally, I would like to thank Sude for her dedication on studying. And she will talk about an interesting topic, the interior angles of a triangle.
First of all, I'd like to thank my mentor and their key. Today we are talking about interior angles of a triangle. Firstly, if I ask you what is the total interior angle of this triangle, what's your answer?
It's pi.
Yes, I for this, we use the cosine formula. That means we see edge AB as a vector AB and edge BC as a vector 2. And cosine B equal the inner product of AB times AB and BC divided by the norm of AB times BC. For this, we use the property of metric space. But if I draw a triangle on the side, what would you think about this part? Okay. If we consider the interior angle as 90 degrees for all interior angle, the total interior angle becomes 270. That means for all triangle has not same interior angle. In this presentation, we're talking about this, and we will follow this outline. Firstly, in the first part, we define manifold, smooth manifold, and Riemannian manifold for obtain a metric construction on the sphere, because there is no vector on the sphere, and I want to use formula cosine formula. And the second part, we define curvature. Actually, we first define curve, then we use its curvature, because I use the curve when I draw a triangle. And the second part, we will add a restriction on this curve, and we will obtain geodesic. And with geodesic, we define geodesic polygon. Then the last one, we will use Gauss-Bonnet theorem for find the interior angle of this triangle. Manifold is a topological space that looks like locally an Euclidean. For example, the Earth. When I look around, I see it as a plane. So there's a good one, for example. But manifold is not enough for construct a vector space. or do calculus. So I want a smooth structure to obtain a derivation for the calculus. Then I call it as smooth manifold. There's an example for smooth manifold and non-smooth manifold. In this curve, there is no unique tangent space, so it is not differentiable at every point. So there is no smooth structure. Then it is not smooth manifold. And in this curve, I can take derivative at every point on the manifold. And since I'm in the smooth manifold, I can do derivative. So I have tangent space, and then I have tangent vector for each point x, and I call it txm, and vector v is tangent vector. And since I have tangent vectors, then I can add a metric, or I can obtain a metric structure on this manifold. And I use using the tangent vector, I can use inner product. And Riemannian manifold is a manifold that I have Riemannian metric. And now curve. Suppose gamma is a curve from interval AB to a manifold. From now on, I use manifold instead of Riemannian manifold. And the first derivative of this gamma is called tangent vector, and its magnitude is speed. It's called as speed. And if speed is 1, then tangent vector is called unit tangent vector. And the derivative of tangent vector is called curvature vector. And curvature vector measures the rate of change of t. So, and there's a relation between curvature vector and normal vector on the curve. And that means curvature vector multiple of normal vector, and the coefficient is k, and it is called as kappa, and it's called as curvature. On this curve, gamma is an oriented curve, positive oriented curve, and at that point, t is a tangent vector, and it has same direction with gamma, and n is normal vector, and it is perpendicular to tangent vector, and gamma 2 prime is curvature vector, and it is a multiple of normal vector. Until now, we use the curvature of curve. Now we define curvature of the surface. In the surface, I cut it with a plane, and I'm interested in its intersection. Then its intersection becomes a curve, so I use the same way to curve and curves curvature. Since there is a lot of and its maximum and minimum value gives us some geometric interpretation. That's mean, and we call them as principal curvature. And its product is called Gaussian curvature and denoted by K. In the first picture, if I cut the plane surface with a plane, I have flat curvature. That means there is no curvature, 0, and I have positive directional or positive side curvature. But since its multiplication is 0, then Gaussian curvature is 0. Then second picture, if I cut it with a plane, I obtain two different signs curvature, and its multiplication is less than 0. And I can say that I'm in the hyperbolic plane. And the last one, when I cut it with a plane, I obtain two same directional, same sign curvature, and its multiplication greater than 0. So I can say that I'm in the spherical space. For example, for a cylinder of a radius A, when I cut it with a plane, I obtain a curve became from circle, and I obtain a flat curvature, and its multiplication is 0. So the Gaussian curvature of cylinder is 0. Now we define geodesic. From now on, we use curve. There is no restriction on this. But now we give a restriction. A shortest curve alpha in a surface or in a manifold M is a geodesic if its second derivative is 0. That means it is a straight line. But I might say straight line, but what I mean is not straight line on the plane. For example, if I draw a meridian on the North Pole to South Pole, it is also a straight line for on the spherical surface. But in the R cube, it is not a straight line. For example, from this point to this point, there is an curve with extra curvature, extra curve. But in the second picture, from this point to this point, there is no extra curvature, so it is a geodesic. And since I draw a lot of meridian from North Pole to South Pole, geodesic may not be unique. And suppose gamma is an arbitrary curve, then its second derivative, magnitude of second derivative, is called geodesic curvature, and it measures the fails to be geodesic. That means if it is 0, then I can say that gamma is a geodesic. But if it the greater it is from 0, the further it is being geodesic. And the cosine formula for Riemannian manifold. So I use the tangent vectors for this formula. And the integral of geodesic curvature on the interval AB is called as total geodesic curvature. And it gives us some information. For example, if the interval is 0, then I can say that the curve is geodesic. And I use now consider a polygon. I can see it as a simple closed curve. That means there is no self-intersection. And suppose gamma is an arbitrary curve now. And suppose gamma from AB, interval AB to a manifold. And suppose S0, S1, Si is the vertices of this polygon. Then for each vertices, I can compute the interior angle and jump angle. By the way, suppose on this curve there is an tangent vector. Tangent vector that is approaching from left side on this point, and on this curve there is another tangent vector that is approaching from right side on this point. And with cosine formula, previous formula, I can find the exterior angle epsilon 2. And if I subtract epsilon I from pi, then I obtain interior angle at that point. And for each tangent vector, there is an angle zeta. It is between frame A1 and tangent vector. And the velocity vector t changed its angle by this formula, and the total change in the angle of t given by this formula. And suppose gamma is a closed curve, simple closed curve, then the total change in the angle of t around the gamma is 2 pi. And geodesic polygon. Geodesic polygon is a polygon whose segments are geodesic. For example, this triangle is geodesic. And there is very important theorem, Gauss-Bonnet theorem. Gauss-Bonnet theorem gives us a relation between exterior angle and with this way interior angle actually, and Gaussian curvature and total geodesic curvature. If I use geodesic polygon, then the total geodesic curvature becomes 0. And if I write pi minus beta I instead of epsilon I can obtain a relation between Gaussian curvature and interior angle beta I. We can see it. And what does it mean? If k equals 0, then I'm in the plane, for example. And since I'm interested in triangle, I use 3 for m. And the total interior angle of triangle becomes or equal to pi radians. And if k greater than 0, then I'm in the spherical surface, for example, this triangle. And the total geodesic total angle of this triangle greater than pi radians. And if k less than 0, then I'm in the hyperbolic plane, and the total angle of triangle less than pi radians. The first triangle, it has its total angle, interior angle greater than pi radians, example 217 degrees. And it is a spherical triangle, and this is a triangle, and total interior angles is 180 degrees. And this last one is hyperbolic triangle, and its total angle, interior angles, is less than pi radians. Thanks for your attention.